So we're going to continue from the last problem that I gave you in the last class. That was a calculation-based problem, and we're going to discuss up some stuffs from this three questions that I've given you last class, and we're also going to cover a bit more material regarding overestimation or underestimation. So we're going to see them in time, but for the timing, let's start with what we have at hand. So have a look. So let's have a look at the question that we have had. We had 5 constants given. These are the constants we're going to recur for our calculation. These 3 are for the first 3 are for the specific capacities of different state of water, and they are going to be applicable for cases where the water undergoes temperature change but not state change. And the lower 2, the latent heat via information, are applicable for scenarios or heat exchange cases where the water is going to transition from one state to another. So they are going to be over here. And then we have this question. The couple of things that I'm going to tell you first is that one thing you need to always remember, that hot object is going to lose heat to the cold object. So hot object's temperature is going to fall, cold object's temperature is going to rise. Or uh, colder state is going to be moving towards the hotter state. For example, if your ice is the cooler object, then it's going to slowly start to melt. Whereas your if your water is the warm object, then it's going to slowly start to freeze. If it's a so hot objects are going to lose heat and cold objects are going to gain heat. And one of the thing that I'm going to cover first is this V option, that for any of this kind of mathematical endeavors or questions to be answered, we have to first understand that the assumption that is used for this process calculation is that for this entire calculation process, we had to consider that all the heat that is lost by the warm object was 100% gained by the cold object, which means no heat loss happened to the surrounding or any of the environment. The two objects which are involved in heat exchange process are exclusively these two objects among themselves. No extra heat was added into the system, or no heat was lost to from the system. That's the only logic by which we can work this out. Because if some additional heat is lost to the system or is gained from the system, then calculations are going to be somewhat messed up because we don't have those information available for us. So let's have a go for these one by one. I'm going to try and solve this on the right side. So let's have a look. This question says the specific capacity of, okay, the first question says 2 kg of H2O at 10 degrees Celsius is mixed with 4.3 kg of water at 62 degrees Celsius. What is the final temperature of the H2O? So on the thing that you can see over here, that both of the state of this material, H2O and H2O, is liquid. So that's why they are only asking you to find out the final temperature, because it is obvious you cannot produce ice by mixing 2 different temperature of water. Your water is going to be somewhat over there. So if I just give you a try to show you a visual idea, let's say somewhere over here we have the hot water temperature, which is 62 degrees Celsius, and somewhere below over here we have the cold water temperature. Let's say that is 10 degrees Celsius. Whenever we'll mix this together, the final temperature is going to be somewhere over here. I don't know exactly where. That doesn't necessarily have to be at the midway point, but somewhere over here there should be our final temperature. So the hot object is going to experience temperature drop. The cold object is going to experience temperature rise. So let's assume that this final temperature is 30 degrees Celsius, which is basically our question mark. So we are trying to find out how much is this going to be. So I can write to solve this equation. This is our question number 1A. So might as well provide this thing. So it's a bit thicker line. So I can write that heat is sometimes given by Q, or we could also give it as E. Anyway, it works. It doesn't matter. So I can write that energy given out by hot water should be equals to energy absorbed by cold water. So because this is applicable for temperature change cases, not state change cases. So I'm gonna write up this equation. The hot water mass was so I'm gonna apply this equation MC delta theta for this scenario and MC delta theta for this scenario as well. Now what I need you to understand. So let me just write the MC delta theta in its original form. MC delta theta equals to MC delta theta. I'm not exaggerating the equations over here. I'm only writing the core form, but whenever I'll be placing values, I'll be very careful to apply the appropriate values of the scenario. So so bear with me. What is the mass of the hot water in this case? This was 4.3 kg. So let's write that up. 4.3. The specific capacity of water is 4.2 into 10 to the power 3 joule per kg per Kelvin, which is a constant. So I might as well write 4.2 into 10 to the power 3, that and the temperature drop for the hot water is gonna be from 62 down to theta. So hot water is gonna start from 60 degrees Celsius and it's gonna fall to 30 degrees Celsius. So if this one's delta theta is gonna be 62 minus theta. Now, for this case, I'm not gonna do a final minus initial. I'm actually doing big minus small because I'm trying to only work with numbers over here. But if we want to use the idea of final minus initial, we can also do that. We just have to take care of some direction information and plus and minus regarding heat given out or heat absorbed and something like that, which is not essential for your understanding. So I'm not gonna cloud your judgment by bringing out the plus minus sign. Just I'm doing big minus small to get the total amount of energy involved over here, which is gonna work for our purpose pretty well. As for the cold water, the mass of the cold water was 2 kg. The water in its water state also has the specific capacity that is 4.2 × 10⁻³ kg, 3 joule per kg per Kelvin. So I'm going to place that. And the water's temperature, cold water's temperature is going to rise from 10 to theta. Theta over here is the assumed final temperature. So this one's going to be theta minus 10. Have a look. Once again, I'm doing big minus small just to get this number. So this is the whole equation that we're going to work with. Because both of the states are water, so I can very easily cut these off. I'm not going to need that. And then you just cross multiply, you just multiply and find out the value of the theta. How much are you going to get?
45.5.
So theta becomes 45.5. Did every one of you who actually attended this problem got the same number?
Sir.
45.5 degrees Celsius. Yes, follow.
Sir, ওটা theta minus 10 কেন? Theta plus 10 কেন না?
Because the temperature got changed from theta 10 to theta. So we are trying to find out how much heat was absorbed by this one. So the how much temperature change did occur to the cold water? Was it theta plus 10 degree or theta minus 10 degree? How much temperature change occurred to the water?
Sir, theta minus 10. Yes.
বুঝা গেছে? আচ্ছা. So that's pretty much it for the first problem, which is a very basic thing. So it's a O-level stuff. So not that complicated. আচ্ছা, এটা গেল. I'm gonna move this thing on the other side because I'm gonna be continuously record this question. So I'm gonna select this all up and store it somewhere else. Let's say store it over here. And I'm gonna zoom in and try number 2. So let's try number 2. Have a look at question number 2. Question number 2 might not as well be that difficult, but still, let's have a look what is happening. The question reads that 1.3 kg of H2O at 20 degrees Celsius is mixed with 250 grams of ice at -5 degrees Celsius. Find out the final condition of the mixture. This condition essentially meant to think. Condition in this case is mean composition of the mixture. How much water and how much ice, and also the final temperature of the mixture, which means whenever they're asking you to find out the condition of the mixture, it is important that for you to understand or appreciate the scenario that we might as well come with a situation where we have a mixture of ice and water together, and the final temperature of the mixture might as well be 0 degrees Celsius, because if we have to have ice and water in equilibrium, it is only possible to happen at 0 degrees Celsius. So what we need to find out logically, that is that gonna happen to our scenario or not. So we do not know this because the question doesn't specify that what would be the final state of the whole mixture. So I'm going to try and calculate different values of relevant heat energies to give ourselves an idea whether how much heat energy is going to be relevant for this scenario. So let me try to explain what I'm trying to mean over here. What I need to appreciate is that the hot object is 1.3 kg of H2 at 20 degrees Celsius, and the cold object is 250 grams of ice at -5 degrees Celsius. So typically the way I usually represent this kind of diagrams is that let's say the temperature of water is gonna drop. Hot water is gonna drop from 20 degrees Celsius to a minimum of how much? What is the minimum temperature of the water if it stays at water? The possible minimum is
0
degrees Celsius. In this process, this hot water is going to give out heat. So it's going to give out heat. Let's say I'm going to label this at QH, heat coming out of the hot object. Okay.
Yes, sir.
So that's one information. And so I'm gonna calculate this out in a bit, but what I also need to want you to understand is that how much heat is going to be required for this entire ice to reach to 0 degrees Celsius and to melt as well. If you wonder why melt, because the final temperature, the final state of this water is gonna be 0 degrees Celsius. So what I'm trying to compare is that by taking heat from the hot water, is it gonna be possible for all the ice to melt or not? So if I show you this over here in a figure, the way I prefer to draw this figure, it can look something like this. This is a division line. So is that first -5 degrees Celsius of ice should rise up to temperature of 0 degrees Celsius. That's going to happen first. Try to understand. This is this arrow for below 0 degrees Celsius is supposed to be for ice. Then, so I'm going to calculate out this heat with the appropriate formula, and then this 0 degrees Celsius ice should be converted to 0 degrees Celsius water. I'm not sure whether this is going to happen or not, but I'm going to try to calculate that how much heat is required for both of these together. What I'm trying to find out, if -5 degrees Celsius of 250 gram of ice ultimately rises up to 0 degrees Celsius and then melts up altogether completely, would it be possible for this thing to happen by the heat supplied from the hot water? So let's say together these two processes are going to require, let's say I'm going to label this with green. Let's say together these two processes are going to require that for these two things to happen, they're going to absorb heat. So I'm giving those arrows in the inward direction just to give you a better idea. Let's say they're going to apply QC or Q cooler object, hot, cold, warmer, cooler, less warmer, no, cold. So fine, I'm going to write this as C. So C in this case is essentially meaning that this is the cooler object, cold object. So this is the heat given up, this is the heat absorbed. Oh, sorry, I better as well write given up and absorbed. Hot cold na diye ota dile bhalo hoy. So this would be the heat given up. So QG, and this will be the heat absorbed. So I might as well write QA. That makes the symbolization a bit easier. Symbolizations are not necessary for your problem, but if you use them for a specific type of symbol, you can be efficient in thinking of the math. It's not essential for your mark scoring process, but it is helpful for you to have a better visualization of the problem altogether. So let me try and calculate these two numbers completely. I'm going to tell you in a bit why am I calculating these two numbers differently. There's a reason for this. Okay, if you go for this one, how much would be QG? QG would be applicable for 2 kg of water. So this is the 2. The specific capacity of water is 4.2 into 10 to the power 3. So I'm going to write this up over here.
Sir, what is G?
G is given up. QG means heat given up. QA means heat absorbed.
Okay.
By G and A, I'm meaning that given up or absorbed. Cold object absorbs the heat and the hot object gives up the heat. Yes, Fadmin bolo. কে যেন স্যার বললা? রাফিজ অথবা
স্যার এখানে তো স্যার আমি স্যার
হ্যাঁ ফারদিন বলো।
স্যার আপনার এখানে স্যার 20 ডিগ্রি সেলসিয়াস অফ ওয়াটার তো স্যার স্টেট চেঞ্জ করবে না, শুধু আইসটাই করবে, তাই না?
That we don't, yeah, ideally yes. Ideally yes. Ideally yes, এই জন্য বলতেছি যে whenever this thing is gonna come down to 0 degrees Celsius, it's gonna remain at 0 degrees Celsius. And now if this thing if some part of this water has to convert into ice, then this thing is gonna have to be ice as well. So this is not gonna change state, preferably, but it's not impossible. এটা হইতে পারে, সেরকম এক্সাম্পল দরকার হলে আমি দেখাবো, but ideally it's not gonna change state.
আচ্ছা স্যার একটা एग्जांपल দিন তো পরে স্যার।
আচ্ছা ঠিক আছে, পরে দেখাবো, আমি সমস্যা নেই। We have to
thank you sir.
some extreme
স্যার এখানে 2 আসলো কিভাবে? এক সেকেন্ড, 1.3 কেজি না?
Oh sorry, my bad. আমি যে আগের কোশ্চেনটা আনসার দিলাম। Thank you শুভ, I'm sorry. So 1.3 এটা কত আসে একটু বলো তো আমাকে, এই ভ্যালুটা কত আসে someone in standard form please. Give me all the decimal values because this is a in between working number. All the decimal values.
Sir, it's 1.092 into 10 to the power 5.
Sir, I don't think it's 1 point. It's just 109200. Oh, in standard form. Sorry, sir.
Yeah, standard form.
ঠিক আছে?
হ্যাঁ,
জি স্যার ঠিক আছে।
10 to the power 5.
হ্যাঁ 10 to the power 5.
আচ্ছা, So this means for the process of 20 degrees Celsius of hot water to cool down to 0 degrees Celsius water, we're gonna require this hot water can give up a maximum of this much energy. Now we're gonna try and calculate how much is the total energy that could be absorbed by the cold water by these two processes. Now, important for you to understand that in this case, first the ice has to increase its temperature from -5 to 0. So for this process, we're gonna have to use MC delta theta. And for this process, we're gonna considering melting because I'm showing the change state as horizontal arrows. So temperature is remaining constant. So for this process, we have to use Q equals to MLF, mass into latent heat of fusion. So if you go for that step, let me do this in two different steps. Well, I can write in general MC delta theta. I'm just starting this equation to make some sense with you. Plus MLF. Now, what I can essentially ensure that this mass that we are working with is the same for the ice mass. So I can pretty much take the mass common from both of these parts because we are working with the same amount of mass. How much mass was that? This was 0.25 kg of ice. Important that we have to place it into SI unit because every other constant is also given in SI unit. So we might as well consider that. So I'm going to take over here 0.25 as common. But if you don't want to take it as common, you can write it as a whole as well. So I'm just going to take it as common because I like to do it that way. So 4.2 into 10 to the power 3 into 0 minus -5. Why 0 minus -5?
Where's the difference?
Sir, difference and it's big minus small.
Exactly. I'm trying to calculate the difference. I'm not trying to calculate the. I don't want negative values over here, so I did big minus small. Exactly. So this is the part of the MC delta theta plus LF because I'm M take to common FLC. I took the M out as common, so I'm going to place the value of latent heat of fusion of ice, which is 3.4 into 10 to the power 5 joule per kg. So this is gonna be 3.45 na 4 I take as 3.4 into 10 to the power 5. So have a go at this number and give me the total value. Actually এই জিনিসটা আমার ভুল হলো, এই জিনিসটা আমি এখানে করাটা ভুল হইছে, এইভাবে করা ঠিক হয় নাই। কেন ঠিক হয় না আমি একটু পরে বলবো। Actually এভাবে করলে আমার লেখা কম হইতেছে, but this is not beneficial for me for the next step. So what can I do? আমি বলতেছি একটু পরে। hold up আমি কেন এটা মুছে করতেছি আমি একটু পরে বলবো। মানে কমন নিয়ে করলে ভালো হইতো, আই প্রেফার দ্যাট ওয়ে, বাট এখানে কমন নিয়ে কেন করতেছি না সেটা আমি একটু পরে এক্সপ্লেইন করব, জাস্ট গিভ মি সাম টাইম। Might as well erase that bracket, we don't need that. I'm gonna write 0.25 again. এটা কত আসে দেখো তো, দুইটা ভ্যালু ইন্ডিভিজুয়ালি বলো আমাকে, তারপর সামটা বলো। give me these numbers in standard form as well. এটা স্ট্যান্ডার্ড ফর্মে কত আসে including all the decimal places?
Sir, energy absorbed হবে না এখানে, energy absorbed by the ice না?
Yeah, ice and if ice melts into water completely, আমি দুইটা হিসাব করতেছি।
E should be 2.1 into 10 to the power 3, shouldn't it be?
এটা কত আসে আমাকে একটু বলো, এটা ক্যালকুলেশন করে দেখো কত আসে।
5250 if you 5.25 into 10 to the power 3.
5.25 into 10 to the power 3.
But sir,
and this one একটু দাঁড়াও আসতেছে, আমি কোশ্চেন আনসার, তোমার কোশ্চেন আনসার পেয়ে যাবা, একটু ওয়েট করো। কত?
850
850 স্ট্যান্ডার্ড ফর্ম লেখার দরকার নাই এখন। now if we so I have a reason to add these numbers in
sir I think it's 85,000.
স্যার এত কম হওয়ার কথা না স্যার।
Oh sorry sir, 10 to the power 5 টা দেখি না, sorry।
85,000
8.5 into 10 power 4.
আচ্ছা এই দুটো আলাদা
জি
করে
স্যার 85000 স্যার।
ওকে ফাইন, এখন দুটোকে অ্যাড করে দেখো কত আসে।
স্যার 9.025 into 10 to the power 4.
sir, may I ask the question now?
বলো।
Sir, why did we use the specific heat capacity of water and not ice?
আচ্ছা আমি ভুল করছি বলবান আই মেড এ গ্রেভ মিস্টেক রায়া থ্যাংক ইউ এটা আইসেরটার জন্য কত 2.1
তো ওয়াটারটা ইউজ করতে হবে না
না এই স্টেটটা তো আইস আমি ভুল লিখছিলাম এই স্টেটটা তো
ও
ওয়াটার
আচ্ছা 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 আচ্ছা
সো এটা ভুল হইছে এটা কত
স্যার
হয়
মানে এইখানে এনার্জি চেঞ্জ একটা পার্টিকুলার হয়ে তারপর আবার হচ্ছে ফিউশনও হচ্ছে
হ্যাঁ
তো আলাদা করে
আমি
করতে হচ্ছে
ওটা ওই জন্য 2.1 হবে হ্যাঁ রায়া ঠিক বলছো এই ভ্যালুটা কত আসে আরেকবার ক্যালকুলেট করো রিক্যালকুলেট করো তো
0.25 into 10 to the power 3.
কত
2
0.625. 0.625.
26,025
2.625, sir. Into 10 to the power 3.
225
26,025
2625
2625. That's the number.
225
স্যার মাঝখানে জিরো হবে না, দ্যাট ইজ ইট।
26,250
না 2600
স্যার 2625 হবে তাই না
হ্যাঁ ঠিক আছে আচ্ছা এখন সামটা বলো সামটা কত আসে I'm sorry I messed up this thing I didn't look for this এই যে দেখো এই ভুলগুলো এখন আমার হচ্ছে এই ভুলগুলো স্টুডেন্টদের খুব কমনলি হয় so you be careful about this এটা সাম করলে কত আসে
8.7625 into 10 to the power 4 joules.
তাহলে তো আমি 8.87625 লিখলেই হয় আচ্ছা আমি এখানে আমার স্ট্যান্ডার্ড ফর্ম লেখার বদলাশন না করলে সমস্যা নেই because these are in between numbers ultimately final answer তুমি স্ট্যান্ডার্ড ফর্মে লিখবা যদি বড় বা ছোট নাম্বার হয় so if you want you can write all of these numbers in full digits as well because these are your in between working values you are allowed to do that so 87625
হ্যাঁ into হ্যাঁ 87625 joules.
joules আর এটা হয়েছিল কত 1092
0
0 10 to the power 5 তো
হ্যাঁ
হবে ঠিক আছে
জি
এখন দেখো আমাদের now have a look at the two value of the energies which one is bigger energy which energy is
Sorry,
bigger
the left one. The left one.
the left one is bigger which means the cold or the warm object will not essentially give out all of its heat energy it doesn't have to because it only have to spend this much energy to make the whole thing right the ice temperature to reach to 0 degrees Celsius heat up the ice to 0 degrees Celsius and then to melt the ice to completely into water it is going to spend this much energy so it means that from the available heat from the hot object we can melt all of the substance that we have this proves that our final state of the mixture is going to be completely water try to appreciate this logic first all the heat energy that you have available from the hot water can be utilized to make the entire ice temperature rise from -5 to 0 and also completely melt and you'd also have some energy left which means all the ice would be melt can you appreciate that
yes sir
everyone please comply that can you appreciate this
Yes, sir.
all the ice will
Yes,
be melt এই স্টেটমেন্টটা অ্যাকসেপ্ট করা যাচ্ছে কিনা লজিক্যালি ওই এই স্টেটমেন্টটাতে আসার জন্য আমি এই ঝামেলাটা করছি ঠিক আছে এখন আমি বাকি কাজটা খুব সিম্পলি করতে পারবো বাকি কাজ সিম্পলি যেটা করব সেটা হচ্ছে I'm going to draw up this whole figure one more time and I can go ahead to do the calculation in two different ways so I'm going to show you two different ways from this point further so let's say so মনে করো তুমি এইটুকু ক্যালকুলেশন আগে করছো and then আচ্ছা এখানে আরেকটা জিনিস তোমাদেরকে বলে দেই before I go further if the question already tells you over here other than using that this vague term condition if the question tells you what is the individual mass of water and ice in the mixture and the final temperature in that case the question already stipulates that there will be some ice remaining in that case you do not have to do this step but if the question says something like this what is the final condition of the mixture you preferably have to do this step to go for to understand what is going to be our calculations can be different than this which I'm going to show you in number 3 as well and some other problem which is going to pop up into this class as well so if I go ahead and try to draw two different ways so the first way I can draw this figure one more time for that temperature change thing. Let's say our initial hot water temperature was 20 degrees Celsius. Let's say the final temperature of the mixture is gonna be theta degrees Celsius. Let's say that theta degrees Celsius is over here, which I want to find out. And this is our 0 degrees Celsius. 0 degrees Celsius would happen from ice to be melt from 0 degrees Celsius ice. So this is what I mean ice, this is what I mean water. And this thing should come from -5 degrees Celsius. ঠিক আছে? এখন আমি এই ক্যালকুলেশনটুকু অনেক ইজিলি করতে পারবো। অনেক ইজিলি কিভাবে করতে পারবো? Have a look. I have calculated this too much energy amount already, haven't I?
Yes, sir.
I know the total sum of this much process. What I do not know is this much, and what I do not know is this much. So I'm gonna only do the calculation for these two parts exclusively. I'm gonna quote the values of these two processes from this calculation. So if I just, for your understanding, if I just label these individual calculations of energy by segment, let's say 1, segment 2, segment 3, segment 4. What I need you to appreciate that segment 1 represents heat given up, segment 2, 3, 4, or in the sequence of time sequence 4, 3, 2, they all represent heat absorbed. So I know the 4 plus 3, I do not know 1 and 2. So what I can write in this case, Q1 should be equals to Q2 plus
আর এক সেকেন্ড হিট অ্যাবসর্ব কোনটার জন্য বললেন?
heat absorb হচ্ছে cold object এর জন্য. So the ice that was over here, it is gonna raise its temperature from -5 to 0 degrees Celsius ice. Then 0 degrees Celsius ice is gonna melt completely into 0 degrees Celsius water. Then that remaining water is gonna have its temperature increased all the way to the final unknown temperature, which we are trying to calculate. So for all of these 3 steps, the cold object is gonna absorb heat, where the hot object is gonna lose heat from 20 degrees Celsius to 30 degrees Celsius. The reason that we are assuming that this final temperature should be in this region is because of this logic, because you can see that the final temperature of the mixture, this ice will be completely melt and it would still have some heat remaining, which means remaining heat দিয়ে সে total mixtureটাকে সে কি করবে? Heat up করবে. So this is the simpler process where we do not have redundancy, but there is another process which I'm going to show you, which will have some redundant calculation to make sense with it. So এখন যদি আমি এখানে ক্যালকুলেশনটা করি, how this calculation is going to work out. How much was the mass of the cold water? So hot water was 1.3 kg. So I'm going to write this whole equation. So this is going to be কত ছিল জানো এখানে? 1.3 into 4.2 into 10 to the power 3 into 20 minus theta. Eta একটা should be equals to, now I do not know how much is Q2, so I'm going to write Q2 in the form of unknown. How much was the mass of the ice? 250 gram, right? So this amount of water that's going to heat up, the mass of this water exclusively is going to be 250 grams. So I might as well write 0.250 multiplied by 4.2. এখন আর 2.1 হবে না, because now this has already converted into water into 10 to the power 3 into theta minus 0. And then I'm going to add up this whole amount of energy. I'm not going to write this whole calculation, but you can write if you want. So I'm going to just simply add up the Q3 plus Q4, which I have calculated earlier, which is 87,625. Everyone, take some time, do the multiplication properly, and get me the value of theta. You might as well have to do 2-3 lines. Do those, and give me the number of theta in 3SF.
Is it 3.31?
Okay, that's your value. So one of your
স্যার
classmates.
-5 থেকে 0 তে যে উঠছে এই পুরোটাই তো 87625 এর মধ্যে কভার হয়ে যাচ্ছে, রাইট?
Yes, ওটুকু হচ্ছে 2625. আর 0 থেকে যে 0 তে মেল্ট হচ্ছে ওটা হচ্ছে এইটুকু। সো এই দুইটাকে সাম করলে এটা হচ্ছে, সো ওই জন্য পুরোটা একবার লিখে দিছি। মানে Q3 plus Q4 পুরোটুকু মিলে হচ্ছে এটা। বলো।
স্যার আমি তো লাইক আচ্ছা ফাইনাল মিক্সচার টেম্পারেচারটা কি সেমই থাকবে, লাইক আপনার আইস মানে আপনার যে আপনার স্টেট চেঞ্জ যখন হলো
হুম।
ওখান থেকে যে থিটার ভ্যালু পর্যন্ত গেল, আর আপনার ওয়াটারটা যে 20 ডিগ্রি থেকে থিটা ভ্যালু, মানে দুইটা একদম পুরো মানে ওই ভ্যালুতে আসবে স্যার।
That's the whole point of equilibrium. Whenever equilibrium will be achieved, all the objects in the mixture will have that same temperature. Not essentially the same state, but they will definitely have the same temperature. Because equilibrium
Sir,
essentially means where the heat transfer process would stop. Not stop period, it would be equal on both directions. Equilibrium, by equilibrium for heat transfer process we mean something like the equilibrium point of a reversible reaction. The heat transfer did not actually stop, but the amount of heat transfer in both directions have become equal, something like that.
Okay, sir, I have another question. Sir, আপনার হচ্ছে কি যে আপনি Q2 তে স্যার,
Yes.
স্যার Q2 তে কি আমি পুরো মিক্সচার ম্যাচটা নিব না? Because
না।
as you're saying, like
Try to
it's a different process তাই দেখে।
Try to understand, the 2 is happening from the 2 is applicable for the water that was created from the melting of ice. How much is that water?
স্যার বুঝছি স্যার, এখন বুঝছি।
3 point কত বলছিল? 31.
জি
দেখো সবাই দেখো এই ভ্যালুটা আসছে
জি
কিনা।
স্যার 314 আসে স্যার আসে।
তো 3s এর 3.31 হলো 3.14 3.31 3s এর ভ্যালু লিখলে 3.31 হলে হবে। So this is one way to solve the problem. এই স্টেপটা বুঝাই গেছে কিনা? আমি একটু জুম আউট করতেছি, সবাই একটু পুরো সামটা দেখো, see if it makes sense. There is another alternative way which I'm going to show you that will have some redundancies.
আপনারা মাইক্রোসফট হোয়াইট বোর্ড ইউজ করতেন হঠাৎ করে?
হ্যাঁ, আমি ইউজুয়ালি মাইক্রোসফট ওয়ার্ড বোর্ডে ফেরত যাবো। যে আজকে আমি বড় একটা কিনছি, কি বলে রাইট প্যাড কিনছি, যেটা দিয়ে আমার ওয়ার্কিং আরো ইজিয়ার হওয়ার কথা, ড্রয়িংস গুলো আরো বিউটিফুল হওয়ার কথা, বিকজ it has the software of this new thing is capable to it is capable to detect geometric shapes and draw them properly. So if I draw a circle, it's gonna become a perfect circle. If I draw a triangle, it's gonna become a perfect triangle at that orientation. And
Sir, is it Wacom or is it another brand?
no, it's Huion.
Oh, Huion, it's good too.
Yeah, I got the purple red color, so I definitely ordered it. They also had the black one, but black is black and black is so common, so why not purple? And also for my new phone that I have bought, Xiaomi Note 8, I also got the Pacific Blue version, which I like. I think they use this extra word before red and blue exclusively for women. Like for men, red, beautiful red. I mean, blue. I mean, Pacific blue, ice blue, electric blue, and then crimson red. Ito jano ki red bollam eta?
Purple red or something.
Something like that. So they use this one extra word before the main color, and that's just so confusing.
That is confusing. There are differences between shades. So obviously, suppose apple red and blood red are not the same thing.
I mean, what I can essentially quote in this case that women have এটা কোত্থেকে আসলো divorce that what I can say that women have different products for different purpose, like, but we men have one thing that's called shower gel, works for everything, hair, body, dishwashing, cleaning.
We can.
So yeah, that was my point. Words, numbers, colors today. No, I mean the numbers which are defined by colors, it has a very good purpose, to be honest. It also in the sequence for CMYK or RGB version, you can specify a specific color without actually having mismatching of information. I mean, let's say what you can see in your monitor as one color might come out in the printing press as a different color depending on the background of your white paper. So if you write to your publisher that this location is going to be this number color, if you give the codes, they know exactly what to print out. So, but if you would give them the color perception for different eyes is also different. So that's basically a thing. Okay, anyway, let's not get there. I'm going to cover the extra part of this explanation. What I want to discuss further is that the other way, I mean, in this whole process, I did not use this information. Did I use this information? Have a look. In this calculation. Hold on, দেখো. In this calculation, I did not use, the 10,920 joule of information. So is there any way we can use this information? There is. And the process to use that information can follow in this manner. Have a look. If we assume that we have mixtured these two objects, and let's assume the entire temperature of this mixture, listen to me. Let's say the entire temperature of that mixture was brought down to 0 degrees Celsius. Understand this part first. Let's say the entire temperature of this thing was brought down to 0 degrees Celsius. Please hold up a second. Okay. The other thing that I can go for to utilize this information is that what we did calculate for this process is that we brought down the temperature of this whole water to 0 degrees Celsius, and we just calculated how much heat would be absorbed to bring it up to this much temperature. Let's say that actually happened. Hypothetically, it's not going to happen. The final temperature is going to be 3.31 degrees Celsius, but let's assume this is going to happen. Now, if this was to happen, you would have the difference of this much heat energy available to you. The hot object is gonna give up this much energy to the water ice amount to bring its temperature to 0 and to melt it at 0 degrees Celsius. And let's say if the hot object was brought down to 0 degrees Celsius, in that case also, it would have given up this much energy, but it doesn't. But if we assume that it was brought down to 0 degrees Celsius, then you would have the difference of these two value amount of energy left. So give me the difference of these two energy. I'm going to do the math and it's going to make sense to you in a bit. For the time being, just keep dumb. Have a look. What is the difference of these two amount of energies? If you do the subtraction.
21575.
21575,
yes, 21575.
575 joule. So let's say we have this amount of joule this amount of joule of energy available to us. If we assume the temperature of the mixture is actually 0 degrees Celsius, but it is not going to be 0 degrees Celsius because we still have some amount of energy left. So this amount of energy is going to be responsible to increase the temperature higher. Now the question that I really want you to appreciate, in this case, we consider that both of the objects were brought down to 0 degrees Celsius. So how much water would have been available at the 0 degrees Celsius? Would it be only 1.3 kg, or would it be only 0.250 kg, or would it be the sum of these two amounts?
Sum of these two amounts.
The total amount of water that we have available is this much amount. So if I now go for the formula, Q equals to mc delta theta for this total amount of water, we can also find out 3.31 by doing a very specific mechanism. So the amount of remaining heat is 21575. The total amount of water that we're trying to heat up is how much? 1.3 plus.
Difference বের করে করতেছেন.
This is a redundant method, which is not essential for you to understand. If you understand this much, it's really okay. But I'm trying to make sense that how could you possibly use this number? 1.3 plus 0.25. Let me zoom it out because I cannot write in this small format. It's difficult. (1.3 plus 0.250 into 4.2 into 10 to the power 3 multiplied by, let's say the unknown temperature is 30 degrees Celsius minus 0. এই কোশ্চেন থেকে থিটা বের করে দেখো তো কত আসে?
Sir.
3.31.
Do you get the same number?
Yes.
You should. So you could also go ahead and do this, do the whole math in this manner as well. What I want you to want you to appreciate that the amount of calculation volume is much too smaller in this step compared to here. Do you see that? How many things did you do? Quite a good number of things.
কিন্তু স্যার রাইট সাইডেটাতে তো ভাবতে হয় বেশি।
হ্যাঁ, exactly the point. I mean, here in this scenario, you have to think more, write less. For this scenario, you have to think less, write more. So whatever suits your brain. আমি
স্যার
দুইটাই দেখালাম,
আপনি
তোমাকে দুইটাই শেখা
স্যার
লাগবে না। তুমি একটা যদি প্রপারলি বুঝো, একটাই মাথায় রাখো। You can absorb only one and go ahead and use that process throughout your whole experience. No big deal.
স্যার একটু
I'm
রিক্যাপ করতে পারবেন?
representing both of them.
হ্যাঁ স্যার, স্যার একটু রাইট সাইডে রিক্যাপ করতে পারবেন স্যার?
আচ্ছা, what I'm trying to tell you is that hypothetically, I'm assuming that I brought down the temperature of this hot water down to 0 degrees Celsius, and this was melted only. So now I'm assuming that this thing did give up 10,900 joule up, and this did absorb this much energy, and this one's temperature is also 0 degrees Celsius. This one is also have converted to 0 degrees Celsius water, which means the final temperature after this much given up heat and this much absorbed heat is 0 degrees Celsius for both of them. So we now have a common temperature for both the mixed objects, which is 0 degrees Celsius, but we are still going to have some amount of heat left, because the idea was that hot object is going to give up heat and cold object is going to absorb heat, and eventually the amount of heat exchange, heat loss by heat loss and heat gain would be equal. But if we consider that this object was brought down to 0 degrees Celsius, all the heat that would have been given up by the hot object would not be absorbed by the cold object. How much heat would we have left? We would have left this much energy left, right?
2157.
21575. This amount of energy, heat energy, we would have left, which means the actual temperature of the mixture would not have been at 0 degrees Celsius, because using this amount of heat, we would be able to increase the temperature of that 0 degrees Celsius mixture of water coming from both the objects to a much higher value. So we just calculated and found out what would be that higher temperature. So use that amount of heat to heat up the total amount of water that we have. That's 1.3 plus 0.250, and found out that how much higher above 0 degrees Celsius this mixture is going to rise. So if I give you some arrows, it's going to be a bit more clear. Try to understand. For this process, we only did the very basic thing, that 20 degrees Celsius dropped to theta, and this one rose up to here. Whereas for this second step, what we are assuming that, let me draw that, those arrows with, let's say, dark blue. So let's say what I'm doing over here, I assume that this one was raised from here up to here properly. Let me choose a thicker line. And this one was brought down to here all the way. So that much calculation was done for this amount of heat energy calculation. Then I consider that this entire amount of heat energy, I'm not sure this would be done, this entire amount of combined amount of water was raised up to that 0 degrees Celsius. That's the calculation I did in the second part.
So sir, আপনার হচ্ছে কি লাইক প্রথমে দুইটা জিনিসে 0 ডিগ্রি সেলসিয়াসে এনে তারপরে যে হিট রিমেইনিং ছিল ওইটা দিয়ে আবার মিক্সচার টেম্পারেচারটা বাড়ছে।
এক্স্যাক্টলি।
ও আচ্ছা স্যার, বুঝেছি, থ্যাংক ইউ স্যার।
এই স্টেপটা কি বুঝা গেছে বলা? মানে এই স্টেপটার আর একটা ফার্দার ইমপ্লিকেশন পরের ম্যাথে আসবে। সো I mean, even though if you don't like this method, I would appreciate that if you understand this method.
I like the second method better.
আচ্ছা, এটার আরেকটা ইমপ্লিকেশন হচ্ছে কিরকম, যেটা আমরা পরের ম্যাথটাতে দেখবো। আমি জাস্ট একটু থিওরিটিক্যালি আলাপ করতেছি, then I'm going to go for the calculation for the second one. That is, let's say in a certain scenario, have a look at these two numbers. In a certain scenario, if these two numbers were different in a way that this one would be smaller and this one would be bigger, then what would have meant? What would that have meant? That is, in this scenario, we're going to come across our number 3 problem. So I'm going to try and describe that for you. And to do this, number 1 ta gelo koi? Ase number 1. Number 1 you took.
So left 45.
Number 1 I took, ঠিক না?
Yes.
বাকি পুরোটা হচ্ছে number 2. Fine. So I'm going to try and remove number 2 from here. Wow, marginally I got the So let's say I'm going to place the whole thing over here. And now I'm going to try to solve number 3. So let's have a look. Number 3. Have a look. 2 kg of water at 10 degrees Celsius is mixed with 1.5 kg of ice at 0 degrees Celsius. Find the final condition of the mixture. So in this case, the ice was at 0 degrees Celsius, which means ice temperature increase is not going to be involved. So ice is only going to melt. So what we can do for this scenario, let's try and calculate this thing. So let's see, this is number 3. 2 kg of water at 10 degrees Celsius. So let's first calculate how much heat can be given up from the water. So Q given up can be a maximum of 2 into 4.2 into 10 to the power 3 multiplied by 10 minus 0. It has become 8, 4, 1, 2, 3, 4. 1, 2, 3, 4. ঠিক আছে? This many joules can be given up by the hot water. আচ্ছা না, এখানে 0 একটা কম হয়, এটা 4.2 ছিলাম, 42 দিতেছিলাম। 0 একটা কম হবে। Have a look. Is this all right?
Yes, sir.
I hope so. And then we have how much ice to melt? 1.5 kg of ice to melt. So let's have a try and calculate how much heat energy would be needed to melt the ice. Let's say the Q absorbed is gonna be 1.5 into 3.4 into 10 to the power 5 joule. How much do you get from here? I cannot do this mentally.
5 1 then 4 0.
Now have a look over here. Have a look. In this scenario, if you want to melt all the ice, you're going to require this much heat, but the hot water can only give you this much heat. So you can see that obviously this would imply that all the ice would not melt, would it?
No.
All the water would not melt. So we can simply try and calculate how much water would be melting if we use this much heat completely. So
স্যার ওয়াটার ফ্রিজ করতে শুরু করবে না?
water, I'm বলতেছি, you try to visualize this process. Try to visualize this process in your head, or I might as well try to draw this. Let's say in a beaker, you have the ice cubes. ঠিক আছে, 1.5 kg of ice cubes, and in another beaker, you have the hot water at 10 degrees Celsius. You just poured in the water. So try to visualize what's going to happen. The hot water's temperature, those molecules temperature is going to start to fall down, and ice from here is going to start to leak out. Leak out means it's going to melt and convert into water. And initially the temperature of those leaked out water is going to be get a bit higher, but when the whole thing would come to equilibrium, when both of the temperatures are going to become equal, the entire water available in the beaker would remain at 0 degrees Celsius, and you would still have some ice remaining. So water would not be technically become frozen. I'm not using the term water would become frozen because in this case, hot water temperature will drop to 0 degrees Celsius water. And in that process of heat given up from the hot water, that is 20 degrees Celsius to 10 degrees Celsius to 0, some amount of ice would be melted. So if I draw this figure over here, temperature figure, it might as well look like this. So 10 degrees Celsius water is going to drop to 0 degrees Celsius water. And in this process is going to give out heat. So Q given out. And in this process of melting, 0 degrees Celsius of ice will be melted to 0 degrees Celsius of water. But this is not going to happen completely. This is going to happen for partial amount of ice. All the ice would not melt. Final temperature would be 0 degrees Celsius, where you will have a mixture of ice and water. There will be some ice and there will be some water. So in this question, we can essentially understand that the final temperature of the mixture will be 0 degrees Celsius. Can you appreciate this information by just looking at these two numbers? Have a look at this one.
Yes, sir.
কে কিছু শুনতে পারতেছে না?
না স্যার, শুনতে পারতেছিল, ওই যে মাঝখান দিয়ে আপনি চলে গেছিলেন না, ভাবছিল যে আপনি কথা বলতেছেন, শুনতে পারতেছিলাম না।
না, I happen to have 3 new kittens, who I cannot anyhow train them to for proper potty training, and they poop literally almost everywhere in my room. So I'm trying to habituate them outside my house. I feed them outside, I give them food outside. They scream a lot to get inside, and they got a chance somehow to get in, and they entered, and within 2 minutes one of them started to poop at the location they prefer to poop. So I had to stop that and throw them out again.
Oh dear.
It's not humane, you might say, but it's also not humane for me to succumb to shit smell continuously.
স্যার ওই সাদাটা আবার বাচ্চা দিছে
তার কাজই একটা।
সেট এই টাইপের একটা বিড়ালের জন্যই এখন আমার বিড়াল আর ভালো লাগে না।
Well, you could have them processed that stops them. I forget the word all the times. That stops them.
হ্যাঁ, মানে বাসে একটা বিড়াল ছিল, পাশের বাসার আর কি, সারাক্ষণ শুধু ওই পুপিংটা করতো, মানে আমাদের বাসার সামনে এসে পুপিংটা করতো, আর তার বাচ্চা কাচ্চা নিয়ে সব নিয়ে আমাদের বাসার সামনে ফর নো রিজন।
মানে এগুলারে মানে পটি ট্রেন করানো যায়। সমস্যা হচ্ছে কি যে মানে একটা থাকলে একটাকে খুব ইজিলি পটি ট্রেন করানো যায়। Whenever you have two, that's a pretty difficult situation, because once you make one of them a habit to be grown up, then the other one, which maybe you are not looking too much, then other one randomly puts in a location. Now if you do not clean that up immediately, or if cleaning up means that cleaning up clean so that they cannot smell that shit in that place anymore. If you don't clean it to that level, it is very much possible that the one that was growing the habit to go into the litter box would start pooping in that location, because it's going to smell shit over there and prefer to shit over there. So, and because I had 3 of those, which are siblings, that became a nightmare for me. I actually tried, and then I don't want to try anymore.
Why don't you employ someone to actually take care of them?
I have people who is continuously helping me to take care of them. That's why I'm still alive. But since it's COVID now, the only person I have is Mamun, and he does a lot of jobs. Cleaning, my clothes washing, cooking for me, and doing the cat stuffs, taking occasional calls. Many of you have received some message over Messenger, send pic, যেখানে চেহারা বোঝা যায়, পাইছো না অনেকে?
না।
আচ্ছা, যারা ফর্ম ফিল আপ করছে, রিসেন্টলি যারা ফর্ম ফিল আপ করছে, they were sent this message, they sent pic. That entire database management is mostly being done by Mamun. I showed him the process. So he's doing a lot. He has a lot on his plate to chew on. Anyway, we're moving on. Is it clear to all of us from these 2 information that the final temperature of the mixture would be 0 degrees Celsius? That's a known scenario, and there would be some ice left and there would be some water remaining. Now the question is, how much ice would be? Because why? Because the coolest object that you have in this case was at 0 degrees Celsius. How can you have, by the mixture of 2 objects, to lower the temperature below the lowest temperature of object? Whenever you mix 2 objects, your final temperature could be somewhere in between.
Oh, acha.
বুঝা গেছে?
হ্যাঁ।
আচ্ছা। So now the question is, how much would be ice and how much would be water? So that can be calculated very easily. What I'm gonna do, I'm gonna use this much heat to calculate out how much ice would be melted. So I'm gonna do this equation: Q given up equals to M into LF. So this would be 84,000 equals to M into 3.4 into 10 to the power 5. এটা দেখো তো কত হয় m এর ভ্যালু?
It's 0.247.
তারপর
247. 247. Wait, 0.24705888235. Yeah, pretty much.
Okay, I wrote this to a good number decibels so that after subtraction we can do the rounding up. So this much ice would be melt. Therefore, remaining ice থাকবে কতটুকু? So therefore, remaining ice কতটুকু হবে?
তো এই অ্যামাউন্টটা মেল্ট অফ করতেছে তো।
Exactly, এই amount melt off হচ্ছে, so how much will be remaining ice?
1.25 kilograms.
So that will be 1.3 minus
1.5.
0.24706, which after
1.5.
round off becomes 1.25 kg.
Sir,
1.5 ছিল।
5 minus 0.24706.
My bad. So 1.25 kg of ice would be remaining after the approximation, and therefore total water that would be would be equals to sum of those two things. How much was the initial amount of water? We had how much water?
2 plus
2 kg.
2 plus 0.24706. This thing, yes. 2.25. Sir, I had a question.
একটু দাঁড়াও। So these three information together, how much ice is remaining in your mixture, and how much water is remaining is available in your mixture, and also the final temperature is what your answer to be. বলো।
স্যার আমি এখানে মানে আরেকভাবে ক্যালকুলেশনটা করেছিলাম। What I did was I took the difference of the energies and হ্যাঁ এখানে ওই যে 510000 minus 84000 equals to m into 3.4 into 10 to the power 5 এটা করলে m এর ভ্যালু হচ্ছে 1.25 kilograms.
Yes.
আমি ক্যালকুলেশনটা করার পর আমি মানে নিজের লজিকটা বুঝতে পারি নাই আর কি ক্যালকুলেশনটা।
Okay. What Raya is asking us is that if we do the difference of these two energies, what we pretty much did in the earlier math, what would that thing mean? Here's the deal. Try to understand what these two information essentially mean. These two information mean that how much would be the given up energy if all of this water was cooled to 0 degrees Celsius, and how much energy would be absorbed by the ice if all of the ice was melted to 0 degrees Celsius of water. These are the two information that we have. Now, if we think hypothetically, let's say the entire hot water got down to 0 degrees Celsius and entire water was melted. In that case, you would have some negative energy available in your system, right? Think about it. Because the total difference of these two energy would give you a negative value. How much is the negative value? This is the heat given up, this is the heat absorbed. So the total amount would have been absorbed. So your amount that would be that should have been absorbed, or you would have the amount of negative energy involved in the system would be how much? Subtraction গুলো কত আসে?
000
কত?
426000.
Now the reason I'm showing this as a negative, because in this case the required absorbed heat is going to be more and the given up heat is supposed to be less. So now you can do one more calculation, is that we can essentially calculate that using this much negative energy, how much water can we freeze? Because hypothetically speaking, this value of energy came into existence assuming that all the ice was melt. So if all the ice was melt, for this scenario, this much of negative energy would be involved in a scenario. Negative energy means that the system would require this much energy more, which it doesn't have available, but we are doing this hypothetically. So using this much energy, how much water could be frozen? So you can do this one equals to MLF, and that basically gives you how much would be the frozen water, and that will also become 1.25 kg.
1.25 kilograms. So basically what we are doing is আমরা মানে 1.5 kilograms ice melt করে যতটুকু এনার্জি পাচ্ছি সেইটুক এনার্জি দিয়ে আমরা কতটুক মানে ওয়াটারকে 0 ডিগ্রি সেলসিয়াসে কুল করে আবার ফ্রিজ করতে পারছি।
Exactly.
Okay, so it actually made sense.
Yep. এই পর্যন্ত বুঝে গেছে সবার? Everyone. আচ্ছা, আরেকটা কোশ্চেন লিখো, বলতেছি আমি। Someone is Now, water is and Abias, water is not essentially doing any freezing here. The hot water is being cooled off to 0 degrees Celsius, and some water is being melted from the ice into 0 degrees Celsius water. There is no freezing happening over here.
So the final temperature of the mixture is just 0 degree water along with some ice, which is at 0 degrees.
Exactly, that's what I wrote over here. That these three information together makes your answer.
Okay.
These information, these three.
Sir,
Yes.
another thing, if the ice and water are in equilibrium, এটা কি এমন হচ্ছে না যে like some of the ice is melting off and some of the water is freezing at the same time, so
Yes.
that's equilibrium?
It's a dynamic equilibrium, but at any point of time, if you measure them individually, you'd get that amount of water and that amount of ice. But you cannot specifically say that the same number of molecules are always remaining at water and the same number of molecules or the same exact molecules. I mean, number, the same exact molecules are always remaining water or the same exact molecules are always remaining ice. That's not the case. There is a continuous interchange between ice state and liquid state because of Brownian motion, but the total amount of water which is getting frozen over a duration of time is the equal number of water of ice molecules which are getting melted into water. So it's a dynamic equilibrium at micro scale or at molecular level.
আচ্ছা, okay, thanks.
স্যার
একটা কোশ্চেন লিখো নাম্বার 4 বলো।
স্যার কোয়েশ্চেন 2 তে আমরা 20 ডিগ্রি থেকে 0 পর্যন্ত করেছি, কিন্তু ওখানে লোয়েস্ট তো -5 ছিল।
Yes.
স্যার -5 পর্যন্ত কেন এনার্জি মানে হিসাব করলাম না?
Because we can see it very well that the object was at -5 degrees, the ice was at -5 degrees Celsius. So if we did have enough cold ice, that I mean, I'm answering to your question in a bit. I mean, the question number 3 ta lekho or 4 ta lekho, you'll get your question answer a bit just a bit later. Write down question number 4. Polaman boltesi 200 gram of water at 15 degrees Celsius. 200 gram of water at 15 degrees Celsius is mixed with 20 kg of
স্যার এক সেকেন্ড আরেকবার একটু রিপিট করেন। লেখা স্টার্ট করতে পারেন
কেন 200 gram of water at 15 degrees Celsius is mixed with 2 kg of ice at -50 degrees Celsius.
Sir, 50 or 15?
50.
50 okay.
হ্যাঁ 50 minus 50
স্যার দুইটাই কি 50 ছিল না একটা 15 আর একটা 50?
প্রথমটা ছিল 15, পরেরটা হচ্ছে -50
15 আর 50
-50
ওই
so
তো
degree Celsius full stop. What is the final condition of the mixture? All right. So let's try and solve this problem. Have a look. In this case, what is the hot object? The 250 gram of water at 50 degrees Celsius is the hot object, and the cold object is 2 kg of water. Water to actually ice about 2 kg of ice is at -50 degrees Celsius. That is the cold object. So the reason we always prefer to calculate up to 0 degrees Celsius, আমি কিন্তু এখনো স্টিমের পার্টটাতে যাই না, স্টিমের পার্টের ক্যালকুলেশনগুলো একটু পরে আলাপ করব আবার। The reason we are essentially doing the calculation up to the 0 degrees Celsius, what we did for number 2, not reached up to -5 degrees Celsius, because we are trying to figure out whether all the mixture would be remaining equilibrium at 0 degrees Celsius or not. That's a variable that we take for judgment. There is no hard and fast rule that has to be taken as a judgment variable, but that's something that we do because that gives us a ease of calculation. So what I mean, a standard is that if we can determine that whether the final mixture is gonna be 0 degrees Celsius or not, then we can very easily go for the calculation. If our logic applies that we have more heat available than required heat, then the mixture temperature is gonna be more than 0 degrees Celsius. If we find out that that available heat from the hot object is less than the heat required by the cold object, then obviously the mixture temperature can be stuck at 0 degrees Celsius. I'm using the word can be because we're gonna see a difference over here right now. Now,
Okay, sir.
try to understand. Okay, good, beautiful. Try to understand one more thing. If we consider the mixture of the 0 degrees Celsius, mixture of these two things has to come to 0 degrees Celsius. First of all, both of the objects have to come to 0 degrees Celsius first, and then there will be a question of freezing or melting. Can you all agree on that first?
Yes, sir.
Both the objects has to first come
Yes,
to 0
sir.
degrees Celsius. Hot objects should cool to 0 degrees Celsius. Cold ice should heat up to 0 degrees Celsius. Only then there can be a question of freezing or melting. So what we can do in this scenario, let's try to calculate out how much heat would be required for their individual temperature increase. So what I'm doing over here, so let's say the hot object was at 15 degrees Celsius. This is going to drop down from 15 to 0 degrees Celsius. We're going to calculate this out differently. And this would be still water. And then we have the ice, which was at 0 degrees, which we are going to calculate to become to 0 degrees Celsius. And the initial temperature was hot. How much? -50 degrees Celsius. So let's calculate out these two heat energies. So how much heat would be required for the water to heat up, or so water to cool down? So Qg, it's just a second. Sorry. So let's calculate out this energy. So let's say Q given up. এটা কত আসে দেখো তো? 0.250. 250 গ্রাম বলছিলাম না 200 গ্রাম বলছিলাম? How much was the mass?
100 gram. 200.
200.
200.
হ্যাঁ ঠিক আছে। So 200 into 4200 into 15 minus 0. এটা কত আসে?
12600.
600. G.
And let's calculate out that if we increase the temperature all the way up over here, only increasing the temperature, we are not even considering melting or freezing over here, because we're going to consider that later, because this temperature gap is pretty large. I can see it pretty large. So I'm going to calculate this amount of energy. Let's say if we do all of this, then how much would be our Q absorbed? Q absorbed would be how much? 2 into 2100. This is ice, not water, into 50 minus 0. Or you could do 0 minus 50. I'm 0 minus 50. That's easier for us to understand for many of our brain. Always big minus small, because we are trying to get non-negative values. এটা কত আসে?
21 তারপর 4টা 0.
So have a look. What is happening? This amount of energy is significantly small compared to this one, which means as this one's temperature is going to rise, this is going to cool off pretty fast. Only after giving up this amount of energy, this whole water is going to come to 0. And then as this one is going to absorb up more energy from this thing, this can start to freeze up. So in this case, what I want you to appreciate, because by comparing this to energy amount, this will happen definitely, and within this time, this will rise up by a small amount. Do you agree?
Yes.
Yes, sir.
So logically, it might also be possible that this might actually freeze up. So let's try and
Wow.
calculate how much heat would be required, how much it would be given up further. So I'm going to write this as QGW. I shouldn't write this as W. I can only calculate, let's say this is process number 1. So let's say QG1. And I'm going to label this as process number 2, let's say. So let's say in this case, we can calculate how much heat could possibly be given up in the process of freezing. So freezing এর জন্য আমাদের formula হচ্ছে MLF, which means 0.200 multiplied by how much? 3.4
into 5.
5. এটা কত আসে দেখো তো?
68000.
স্যার এটা কেমনে পসিবল, লাইক ফ্রিজ কেমনে হবে?
Freeze হবে কারণ হচ্ছে because this is possible to freeze because the cold object that we have in contact is still cool enough, so it is still craving for heat energy, and this object is still at liquid state. So liquid state means it has energy, latent heat within itself. So this object is going to start extracting out that energy from the hot object. You have to understand that this one's this one's temperature is not 0 degree yet. This has gone up by a small amount, because what I told you that this is very small, this is very large. So this is going to drop all the way from 15 to 0, and this is going to only rise up by a small amount, not even close to 0 Celsius.
So like যেগুলো এনার্জি লেফট আছে ওটা আবার এক্সট্রাক্ট করা স্টার্ট করবে যখন কি
হ্যাঁ, condensation. So let's do this, and if you now do a sum of these two numbers, how much do you get over here? Have a sum.
So 1 sorry 2
80600 now.
80600
80600.
So that's the amount of energy you're gonna require for 1 plus 2 completely happening. Does this also equal to this much?
No.
Have a look. Which means all of this water, which was the hot water, it can cool down to 0. That water can freeze up all the way up to 0, and still this thing will not rise up to 0, which means this one's temperature might as well go up a little bit. Let's say up over here. Now you have this frozen water over here, this cold object over here, and then this one is going to start dropping down to an unknown temperature, and this is going to rise up to a certain unknown temperature, and this is going to be a final mixture temperature, which is going to be somewhat below than 0 degrees Celsius. Let's say that temperature is theta degrees Celsius. We want to calculate out how much is this temperature. So from the calculation and the comparison of these energy values, we can essentially decide that the final temperature of this whole mixture is going to be on the negative side of the 0 scale. It is not going to be on the top side. So in this case, melting is not happening, freezing is happening, and those frozen water is going to have its temperature reduced further down, because the cold object that we have given was big in mass. Have a look, try to compare the masses. I gave those numbers in this manner, that you have the cold object ice had a mass of how much? 2 kg, when its temperature was how much? Minus 50 degrees Celsius. Whereas the hot object was only given a mass of only how much? 200 gram, and it has a temperature of minus 15 degrees Celsius. So essentially, the cold object is going to try to absorb more heat compared to the energy given up by the hot object, as if we try to calculate both of them to reach to 0 degrees Celsius, which is not going to happen. So now once again, we can go for our step number 2, or we can directly go for our step number 3. So if you go for step number 2, or the method that we discussed in question number 2, we can do this. We know exactly how much is the total energy absorbed in process 1 plus 2. Do we know this thing? 1 into a total energy absorbed koto? 80600. Let's say this will be our step number 3, our process 3, and this will be our process 4. So what I can write, that heat given up in Q1 plus Q2 plus Q3 should be equal to heat absorbed in Q4. Have a look if you can appreciate this equation by looking at this flow diagram that I'm trying to draw. Can you all appreciate this?
Yes, sir.
Everyone have a look. Total given out by the hot object should be equal to total heat absorbed by the cold object. এটা ঠিক আছে সবাই? দেখো, রেসপন্ড করো।
জি স্যার, ঠিক আছে।
Say something or write something.
Sir, Q3 is equal to Q4 কেন হলো?
Q3 goes to 4 না। Q1 plus Q2
মানে
plus Q3 goes to 4.
মানে Q1 plus Q2 কনসিডার কেন করছেন? মানে হোল প্রসেসটা।
হ্যাঁ, because the total amount of heat given out by the hot object is equal to the heat absorbed by the cold object. That's the basic law that we have discussed for this 1B question. What is the assumption? That heat given out by the hot object is equal to heat absorbed by the cold object, or no heat is gained / lost to or from the surrounding.
Okay, sir. Good. Thank you.
So we can go ahead. I'm going to write in horizontal direction because I don't have much space here. So the sum of Q1 plus Q2 is 80,600. So I'm going to just write this thing over here, 8600. And let's say if to have this happening, we're going to have, this was ice and the mass was only 0.200.
0.2 into 2.1
into 2100 into theta minus 0.
Or should it be 0 minus theta? Because এখানে তাহলে ঝামেলা হওয়ার possibility আছে।
Sir, 0 minus theta হবে না? Big minus small.
Sorry, yeah, 0 minus theta হবে, আমি বলছি। Sorry, it should be 0 minus theta.
It's okay, sir. মানুষ মাত্রই ভুল।
হ্যাঁ, 0 minus
Sir,
theta.
প্লাস হয়ে যাবে স্যার, মানে মাইনাস ব্র্যাকেটে মাইনাস থিটা।
না না,
মানে 0 প্লাস থিটা হবে, কারণ থিটা তো
থিটাটাকে আমি সিম্বল হিসেবে থিটা ভরাচ্ছি, আলটিমেটলি থিটার ভ্যালুটা আসবে নেগেটিভ।
ও,
আমি যদি এখানে মাইনাস থিটা দিয়ে দিই তাহলে আবার এখানে মাইনাস থিটা লিখতে হবে।
স্যার এক সেকেন্ড, 0 মাইনাস থিটা হলো কেন?
Because we are always going to do big minus small. We're trying to find out the total amount of energy without finding out that. So in this case, we logically decided, established that the temperature is going to be smaller than 0 degrees Celsius. So big minus small. This one should be equals to how much? 2 into 2100 into theta minus 50. এইটাকে এখন আস্তে ধীরে সলভ করো। Everyone take some time, do the multiplication and come up with the value of theta. Take your time and slowly calculationটা করে আমাকে ভ্যালু বলো, দেখো কত আসে।
So can I ask a question?
Yes.
Sir, for this problem, are we using judgment to say that none of the ice will melt?
None of the initial ice will melt, yes.
Because such a large mass and such a low temperature. Did we use our judgment to use that, or was there some mathematical logic?
No, there is a mathematical logic. The mathematical logic is very sound here. The mathematical logic is this, that to reduce the temperature of the hot object temperature to 0 degrees Celsius, you need this much, which is not even close to here, which means we can make it to lose more heat. So then we calculate how much heat can be given out in the process for it to become completely frozen to 0 degrees Celsius. We calculated this as well. We can see that this amount of heat energy is also not even equal to this one, which means this object is going to cool down further, because this one can absorb this amount of energy all the way up to 0 degrees Celsius. So if we have to melt some of the available ice that we have initially, first of all, you have to raise this temperature to 0 degrees Celsius. That's the first thing you have to do. After raising the temperature to 0 degrees Celsius, can we think about melting it? But what we can see over here, that the hot object that we have available is only capable to give us 80,600 joule of energy once it itself become completely frozen. So how could you possibly take the temperature of your initial ice amount to 0 degrees Celsius, because that amount of heat is simply not available to your inner system.
I see. So the ice heats up, but it does not even reach the 0 degree value.
That's the whole point. Yes, exactly.
Sir, but some of the water does get converted into ice, doesn't it?
All of the water will convert it into ice, not some.
Oh, yeah.
The entire 200 gram.
কোল্ড কান্ট্রিজে এটাই হয়।
Well, I'd say yes. I mean, these are
এখানে
experimental
গরম পানি ছুঁড়ে মারলে বরফ হয়ে যায়।
স্যার
আচ্ছা,
হয়
হ্যাঁ,
ইউটিউবে
হ্যাঁ, that can make a very large rainbow color thing, মানে rainbow না, ওই যে কি বলে, মানে spiral type of thing, and some people do splash hot water onto them, not understanding what they're doing. There are some fail videos as well. Yeah.
May you provide us with some links, sir?
আমি একটু পরে ভিডিওতে ইউটিউবে দেখাবো না। আগে ক্যাল ম্যাথটা করো, আমাকে থিটার ভ্যালু বলো কত আসে।
Minus
Some of my are
heat,
regarding
28 degrees Celsius.
minus 28 exactly.
Yep. মানে দুইটা decimal place পর 865.
So you might as well write 28.0 just to
Yeah.
make it clear, sir. Minus 28.0 degrees Celsius. So that's our final temperature mixture. So that is also possible for our mathematical process to happen. So are we clear with this? So এইটুকু যখন হইলো, এখন আমাদের ফাইনাল টেম্পারেচার যেহেতু মাইনাস আসছে, সো there is আমাদেরকে আর আলাদা করে স্টেট মিক্সচার করার দরকার নাই. You just have to add up the two masses. This is the final temperature of the mixture you're going to have, and what will be the total mass of the ice? Would this be the total amount of ice?
20.2.
2.2.
Why? 20 kg ছিল না? Wait, there's a calculation mistake. We used 2 kilograms. There should be 20 kilograms.
This was 20.
স্যার 2 ছিল।
স্যার
Sir,
2 ছিল।
sir না 2 বললো।
I say mass 2 ছিল, টেম্পারেচার ছিল -50. এটা কি ভুল হইছে?
না।
স্যার প্রথমে আপনি 20 বলেছিলেন, তারপরে 2 বলেছিলেন, সো ইউ মিক্সড আপ।
So
আচ্ছা, তাহলে my bad. It's I meant it to be 2.
আচ্ছা, okay. Yes, we get it.
আচ্ছা, সো এই ম্যাথটা কি বুঝে গেছে সবার? পুরোটা দেখো একবার সবাই। আমি একটু জুম আউট করি, জুম করে দেখা যাবে না। দেখো পুরো প্রসেসটা দেখো। Now, is there any further thing that you want to talk about, or I can actually discuss two more problems that we can go ahead forward? আচ্ছা, এই টাইপের প্রবলেম আমি তোমাদেরকে মানে the reason I actually showed you this kind of মানে man-made problem, মানে other than washable, I actually made up these problems to give you an understanding how to judge the thermal scenarios. That you have to understand that, I mean, you can never utilize more heat than you have available, and then you have to understand that if you have more heat available, you can actually essentially melt your heat up your cold object. Eventually you can melt it, and if you still have more heat available, you can heat it up to a higher temperature as well. So it all comes down to the point that the whole idea of equilibrium is that equilibrium does not mean equilibrium of state. Equilibrium would always mean equilibrium of temperature. It's your the heat exchange would stop. Stop in not in macro level, not in micro level. Let's say in macro level, or the overall heat exchange will stop when the temperature of both of the mixed objects would become equal. So that was a pretty interesting question. So one of the questions that I would like to ask you, which actually showed up in the MCQ paper of your O-levels mocks, is this question. পড়বো না, একটা MCQ question লিখো। MCQ question হয়তো এটা actually MCQ ছিল, বাট আমি তোমাকে অপশন দিব না, আমি জাস্ট তোমার একটা কোশ্চেন করে বের করবা, লিখো।
স্যার একটা কোশ্চেন ছিল।
লিখেছো? লিখো 60 degrees Celsius of hot water is mixed with 60 degrees Celsius of hot water is mixed with 10 degrees Celsius of cold water.
স্যার একটু রিপিট করবেন?
60 degrees Celsius of hot water is mixed with 10 degrees Celsius of cold water, full stop.
Yes, sir.
Full stop লিখো। Cold water mass is 9 times the mass of hot water.
Wait, is it that MCQ?
It is that MCQ.
Why?
It's a good one. Cold
তুমি তখন
water.
ছিলা?
ও মকের সময় আসছিল।
Cold water mass is 9 times of that.
Cold water mass is 9 times of the mass of hot water. Full stop. What is the final temperature of the mixture?
স্যার আবার একটু রিপিট করবেন, ভালো লাগেছে।
First sentence also is so. I mean, normally we'll see the hot water temperature is 60 degrees Celsius, cold water temperature is 10 degrees Celsius.
না,
Cold water mass is 9 times the mass of hot water. Full stop. What is the final temperature of the mixture? করো এটা ট্রাই করো দেখো কত আসে। I can give you a small bit of hint that you can assume that the hot water mass is M and the cold water mass is 9M. M and M would be cut off from both sides. That way you can get the final temperature a bit more easily because the masses are not specifically defined. So express them in terms of a variable.
15 degrees Celsius?
কত?
15.
Yes, that's the correct response.
Yes, sir, I got 15.
সবার কি 15 আসছে?
Yes, sir.
জি স্যার।
আচ্ছা, এটা 15 আসে, এটা লজিক্যালি মানে কি ইকুয়েশন দিয়ে বের করলে খুব সিম্পল। The equation is gonna look like this. I'm not preferring to write this, but I'm gonna tell you. Q given equals to Q absorbed. Q given এর ফর্মুলা আসবে হচ্ছে M into C. Let's say C is 4.2 into 10⁻³ that will be equal on both sides. So I'm only write C. M into C into 60 minus theta because the hot water temperature is gonna drop. So I'm assuming theta is my final temperature equals to 9M into C into 10 theta minus 10 because the cold water temperature is going to rise. So MC is going to cross off on both sides, and if you do the cross multiplication and do the side change, you're going to find out theta equals to 15 degrees Celsius. That's the mathematical way. Now there is a theoretical way to solve this thing as well. The theoretical way to solve this thing is like this. Try to think about this. Everyone listening to me?
Yes, sir.
Sure. Two of our participants raised our hands, or actually currently one of their raised their hands. Abiaz, okay, I'll give you a question. Wait, I will give you the floor. Wait. What I want you to understand, if you think theoretically, try to get this idea. Whenever you will mix this two amount of water, hot water's temperature will drop and cold water's temperature is going to rise because we have the same substances, water. So their temperature change will be inversely proportional to their masses. Now you might wonder, say what? I'll tell you what. Try to visualize the formula.
Sorry, try. What was that?
Try to visualize the formula. Q equals to M C delta theta. Look it in your imagine this formula. For this scenario of heat exchange, Q given out and Q absorbed is same, which means for both the water amount, Q is equal. So Q is a constant. M is not a constant. C is a constant because they are both water. So because Q is a constant, C is a constant, on the right side you have M and delta theta as product, which means mass and delta theta are gonna be inversely proportional. Do you understand this part?
Yes, sir.
M and delta theta would be inversely proportional because on the right side you have, constant equals to M into constant into delta theta, which means basically I can write M delta theta equals to a constant, which means
Sir,
M,
Q can the constant, sir?
because the heat given up and heat absorbed for both the hot water and the cold water should be exactly equal. Hot water gives up heat, cold water absorbs the same amount of heat.
Oh, okay.
Okay.
মানে আপনার হচ্ছে যখন ইকুইলিব্রিয়াম, রাইট?
হ্যাঁ, after reaching equilibrium, definitely. So because of this, we can pretty much say that after when the equilibrium would be reached, the M and delta would be inversely proportional. This tells you one information. Because the mass of hot water, এই পার্টটা খুব ভালো করে খেয়াল করো. Because the mass of hot water is 1/9 compared to the hot or cold water. So if you think about this, let me give you a ratio. Mass of hot water is to mass of cold water equals to 1:9, right?
Yes, sir.
Kids, try to visualize. Mass of hot water is to mass of cold water equals to 1:9, which would mean delta theta of hot water is to delta theta of cold water should be 9:1 because they were inversely proportional. Which means now try to visualize the temperature line, vertical temperature line. On the top, try to imagine 60 degrees Celsius, at the bottom 10 degrees Celsius. 60 is going to come down by 9 parts, where 10 is going to rise up by 1 part. 60 is going to come down by 9 part, and 10 is going to rise up by 1 part, which means you are going to try to divide this difference into 9:1 ratio. If you do that, you'll find out that location is 15 degrees Celsius. Because you're going to divide the 50-degree difference between 60 and 50 into 9:1 ratio. So the top one is going to drop by 9/10 of that. The bottom one is going to rise by 1/10 of it. 10 কোথা থেকে আসছে বুঝতেছো?
Yes.
বলবান 9:1 এর অ্যাডিশন করে 10 আসতেছে।
মানে স্যার এখানে ইউনিটারি মেথডের মতো অ্যাপ্লাই করা যাবে, রাইট?
Exactly, that's what I'm trying to get in your head. Kids, did you understand this calculation?
Yes, sir.
স্যার আবার যদি আমরা রিপিট করতে পারেন।
আচ্ছা কোন জায়গা থেকে রিপিট করব বলো? ইনভার্সলি প্রপোর্শনাল বলতে বুঝছো? ভার্টিক্যাল লাইনটা থেকে ঝামেলা হচ্ছে, রাইট?
Yeah.
আচ্ছা, try to imagine the temperature line as a vertical line that I have been showing over here for the earlier maths. Imagine on a vertical line, the top level is 60 degrees Celsius, the bottom level is 10 degrees Celsius. What I want you to understand, this 60 degrees Celsius is going to come down and the 10 degrees Celsius is going to rise up in such a way so that the drop amount would be 9 times compared to the rise amount.
Oh, okay.
So you are trying to divide the in-between gap into 9:1 ratio.
Yeah.
That's what gives you the 15 degrees Celsius.
Oh, আচ্ছা বুঝছি স্যার।
Actually pretty simple after you get hold of it, right?
It's simple once you can add up all the Lego pieces.
Yes.
Yeah, বুঝছি স্যার।
Okay, Abias, you have your raised hand. Do you have a question?
Sir, I had a question before that was answered, but I have a new question.
Okay, beautiful, no problem. So that was one of the things. There are two more things which I'd definitely like to discuss in today's class so that we can actually start the worksheet tomorrow. So, but I'm going to pick up those questions from my worksheet. These questions are about a little bit about overestimation and underestimation. Okay, let me just write up this formula and give you this number. Let's say you're trying to measure the latent heat of fusion of ice. What? Latent heat of fusion of ice. So in some method, experimental method, you are going to measure the Q that would be absorbed into the ice, and in some method you're going to measure the M, and you are trying to calculate the LF. So LF would be calculated by the basic equation that heat absorbed by the ice divided by mass of ice that was melted. Now, one of the question that usually comes in the exam hall is that for this kind of situations, and also, as let's say this is one experimental scenario. I'm going to explain two scenarios simultaneously. That's why. So the other scenario is that in a second experiment, let's say in a different experiment, let's say you are trying to measure the latent heat of vaporization of water. So in that case, let's say by some mechanism you have calculated the heat that was required to boil some amount of water, and you have this equation where LV is your unknown. So let's say the equation is LV equals to Q by M. So these are two similar equations, but not the same equation. Now, the question that usually comes in the exam paper is that are the values that which are calculated over here are completely accurate, or is any of this value is an overestimation or underestimation? Now, let me elaborate these two words and try to make sense of it. Try to understand. A number being overestimation means the number that we are calculating is bigger than what it is supposed to be. Overestimation means that what you have calculated is somewhat bigger than what the true value is supposed to be. What the true value is. Underestimation means that your calculated quantity is somewhat smaller compared to what you have done. Now, there are two different ways to process this two information. I'm going to cover both of these. Try to think about this. Standard case scenario, we do the experiment in RTP. What is the temperature of RTP? 25 degrees Celsius. Latent heat of fusion of ice happens at which temperature? 0 degree. Latent heat of vaporization of water happens at which temperature? We know this, right? Now think about it. Whenever we'll do the experiment for the latent heat of vaporization of latent heat of melting of ice, we are going to have some ice cubes in a closed container. We're gonna try to insulate it as best as we can. We're gonna go ahead and provide the heat with some electrical heating mechanism, and then electrical heating mechanism, and this will ultimately give us and this will ultimately give us the Q value, which is the heat energy relevant from our electric heater, and the M would be measured by a beaker, in which we'll be measuring the amount of water ice melted water will be captured over a certain duration of time. Now, try to understand, try to visualize, try to understand this process. No matter how good of an insulation you use, you can never 100% insulate the setup. That's the first thing I want you to appreciate. That's the whole point. That's the whole point of having error sources. I mean, the most common error source for any thermal experiment is heat lost or gained from the surrounding. Now, for the sake of easier visualization, assume that you use no lagging. You used no insulation whatsoever. So what I want you to appreciate that in the process of melting the ice, along with the heat that you are providing from your heater, some extra heat would get added into your melting process from the surrounding, because in this scenario, for the melting scenario of ice is the cooler object compared to the atmosphere. Do you agree?
Yes, sir.
Heat would be getting in your setup. So the amount of heat that you have actually measured and the actual amount of heat that was used to melt the ice, between these two amounts, which one is bigger? The actual amount is bigger or your measured amount is bigger?
The actual amount is bigger.
That's correct. Raya is correct. But can everyone else agree to this? I'm going to say this again. You are going to calculate the amount of heat that you provided using the formula power into time by some electrical heater which was kept in contact with the crushed ice. So that is your Q that was measured from your apparatus setup. But along with this heat, additional to this supplied heat from your electrical heater, some heat would definitely be absorbed from the surrounding as well. This heat that is absorbed from the surrounding will also add to the mass of water that ice that would be melted. Which means the question that I'm asking right now, come again, the actual amount of heat that is being used to melt the ice, is it bigger compared to your calculated heat or smaller?
Bigger, sir.
Sir, it's bigger, sir.
Everyone, please respond. Do you
Sir,
understand
bigger,
that the
bigger.
actual amount is supposed to be
Sir,
bigger?
bigger.
Yes, sir, bigger.
So have a look at this equation. So now if you have a look at this LF value, for the M that you are getting, the Q that you are using a Q value that is smaller than what its actual value is. This proves that LF is an underestimation. Because the numerator that you are using to calculate the value is somewhat what? Somewhat smaller compared to what it is supposed to be. This discussion was made in the term of considering what was the effect on the Q value for the M. There is a reverse version. Reverse version হচ্ছে the amount of heat that we exactly provided from the electric heater that would do some melting. Additional to that melting, surrounding heat would also do some melting, which would not be that heat would not be calculated in our Q value. So the M value or the mass of water that would be dripping out of the funnel, crushed ice funnel, that M value would be bigger compared to what it is supposed to be for our electric heater exclusively. What I'm trying to mean is that if the electric heater was exclusively supposed to melt, let's say 15 grams of ice in a certain duration of time, our actual measured water is gonna be, let's say 17 grams or 18 grams. Because that extra 2 or 3 grams would be melt from the atmosphere. Do I make sense?
স্যার আরেকটা ব্যাপার আছে না যে কন্টেইনারে আমরা তো পুরো হিটটা তো আসলে ইউজড আপ হচ্ছে না বিকজ কন্টেইনার কিছুটা অ্যাবজর্ব করতেছে না
আচ্ছা কন্টেইনারে হিটিং আপ ইফেক্টটা আমরা অ্যাকচুয়ালি সিগনিফিকেন্টলি অ্যাভয়েড করতে পারি the way we avoid that is that we set up the container and allow everything to come into equilibrium over a duration of time. Let's say you have your funnel and beaker and everything, and then you put crushed ice onto the funnel, then you wait for some time to observe a uniform dripping rate out of the funnel. So tip 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 a sequence, I mean the water is going to fall in this sequence. You have to wait out so that falling rate sequence is uniform after you turn on the heater. You cannot turn on the heater and immediately start taking reading. You are going to start taking reading the instance you put the beaker under your funnel and you start taking reading. Then you take out your beaker and you stop your stopwatch. So the stopping and the starting stopwatch would not be dependent on when you turn on the heater and when you turn off the heater. It's not measured that way. I mean, you have to turn up your heater in your setup and allow the melting rate to become uniform. And once you are pretty much convinced that the water dropping rate is quite uniform, you place the beaker at one instant. You place the beaker under the funnel and start your stopwatch. Do I get my point? Do you get my point?
Yes, sir, I get it.
Okay. So that's the details that is inherited embedded in our physical description. But it was a good question. So thank you, Shubho, for the question. So the point I was trying to make that the second way we can go for the equation is that the amount of heat that we did calculate for this equation, the actual mass of water that was melted is actually somewhat bigger because atmospheric heating did also melt some water, which means in this equation, the M is somewhat bigger than what it is supposed to be. Do you agree?
Sir, বুঝি না আরেকবার বলবেন একটু।
The Q is somewhat smaller compared than I mean, if you consider that this M value is correct, then this Q value is somewhat smaller.
Yes, sir.
Which means this fraction is somewhat smaller than the actual value. So this was an
underestimate. মানে M value যদি বেশি হয় তাহলে Q value smaller.
Kids, listen up. I'm telling you the effect of either of these variables, considering the other one correct. So don't mess up the two information simultaneously. Don't mixture them. Like one is tehari, another is kapchi. So they don't mix these up. I'll go again. If I assume that the m value is correct, then I have to say the q value that we're using is smaller than what it's supposed to be, because we could not incorporate the heat that was absorbed from the atmosphere. Because q is a small value than the true value, and the numerator is smaller, means the actual value of the total fraction will also become smaller, which means in this case LF should be an underestimation. This is one set of discussion. This is what it is in the first part. The second part, what I'm covering, if we consider q is correct, then I can say for that exact q, the m value that is at the bottom is somewhat bigger than what it's supposed to be, because in that m value we have heater melted water plus atmosphere melted water. Take this out. বুঝা যাচ্ছে কি বলতেছে?
জি স্যার।
If we consider the q is correct, which means if we really want to calculate the if we consider the heat energy supplied by the electric heater was the exact value of heat that we could supply, then we have to say that but the m value wouldn't have been correct, because additional amount of ice was actually melted by absorbing heat from the surrounding. So if you can either explain the overestimation or underestimation either by the numerator quantity or by the denominator quantity, but either way your answer would be same, because if you consider q is a correct number, in that case m is supposed to be smaller, which means currently m is larger than what it's supposed to be, which means the altogether fraction value is somewhat smaller than the true value, which means LF would be an underestimation.
স্যার যদি m এর ভ্যালু হাই হয়, তার মানে হচ্ছে হিট থেকে মানে সারাউন্ডিং হিট থেকে ওয়াটার মেল্ট হচ্ছে, সরি আইস মেল্ট হচ্ছে, তাহলে
additional ice melt হচ্ছে, additional is বলো
কিউ কিভাবে কারেক্ট থাকে?
না ওটা বলতেছি that if we want to consider that q value is, what I'm trying to tell you is that by using the word correct, choosing the word correct was not a good choice. What I'm trying to mean is that if we want to keep one of the number intact, let's say that's the word, that we have measured a heat energy supply that is q, and we want to use that, and then we want to change the other one. So if I want to keep the q intact, what is the mathematical output of power of the electric heater into time, then I have to use a smaller value of m to get the actual true value of the electric heater fusion of ice, because the amount of water that I have collected in my beaker, all of those water was not made by the exclusive heating of the heater. So in that water, some water does exist which was melt from the surrounding. So if I want to use that intact value of calculated value of q, then m should be somewhat smaller. That's the logic. I shouldn't have used the word correct.
ওকে বুঝছি।
বুঝতে পারছি?
হ্যাঁ স্যার।
Exact wording গুলো তোমরা যখন ওয়ার্কশিট করো মার্কশিট থেকে পিক আপ করতে পারো, নট এ বিগ ডিল, বাট ইজ দ্য কনসেপ্ট মেকিং সেন্স? Everyone, please respond.
Yes, sir.
We still have 42 people in the class. I am talking to like 5-6 people. Everyone else, এই পার্টটুকু বুঝা গেছে কিনা? Yes or no লিখো. If you don't want to talk in the voice channel, write in the message window.
Sir, I understand.
Okay,
Yes,
there are more people left.
স্যার
বলো।
স্যার কিউ যদি আমরা ধরি যে কিউ এর ভ্যালুটা ঠিক আছে, তাহলে এম তো হচ্ছে স্লাইটলি ডিক্রিজ করবে, রাইট?
ডিক্রিজ করা উচিত ছিল, বাট আমাদের মেজারমেন্টে বড় আসবে।
হ্যাঁ। আর যদি স্যার এমটা আমরা ধরি যে কনস্ট্যান্ট, তাহলে কিউ কি হবে স্যার বললেন?
তাহলে কিউটা আরো বড় হওয়া উচিত ছিল, বিকজ ওই পরিমাণ এম মেল্ট করার জন্য যতটুকু হিট লাগছে তার একটা পার্ট হিটার থেকে আসছে, আরেকটা পার্ট অ্যাটমসফিয়ার থেকে আসছে। তার মানে এমটাকে যদি আমরা ইনট্যাক্ট ইউজ করতে চাই, তাহলে আমাদের মেজার করা কিউ এর থেকে বড় একটা কিউ নিউমেরেটর আসা উচিত ছিল। মানে হচ্ছে ফর বোথ অফ দিস ম্যাথমেটিক্যাল derivation we can say that our calculated number is somewhat smaller than what it is supposed to be, because the numerator either had to be bigger or the denominator had to be
মানে
smaller.
LF টা কম আসছে আমাদের স্যার কি
হ্যাঁ, net value টা আমাদের কম আসছে, so this way LF was an underestimation. বুঝে গেছে? Now comes to the second part. The LV, or if we do a second experiment where we're gonna heat up some water using an electrical heater, and we're gonna boil some water and we're gonna measure the amount of mass reduction of the beaker to find out how much water got evaporated out. We're not going to capture the steam. Get the point? This entire setup is gonna be set up onto a measuring scale, and when everything is boiling up at a uniform rate, we're gonna start the stopwatch at a specific instance of mass value. Then we're going to stop the stopwatch at another specific, and after a specific amount of time, and we're going to record the second mass value. Subtracting these two mass values, we're going to calculate out how much water got boiled out. Now, and we're going to calculate that heat amount by multiplying with the power of the electrical heater with the time amount that is relevant. Now, important bit is that, yes.
Sir, in both the previous cases, we were underestimating, right?
Yes, that was my point.
Okay, I got it.
Okay, but for the boiling case, what is going to happen, because this temperature, this working environment temperature for the boiling scenario is 100 degrees Celsius. This temperature is bigger than 25, right? খেয়াল করো, your experimental environment would have a temperature of 100 degrees Celsius, which should be higher than 25 degrees Celsius, which means opposite to your first scenario. In the second scenario, heat would be escaping out to the environment, which means all the heat that you will be providing with your electrical heater, 100% of that heat would not be used up in boiling. Some heat would be lost in the surrounding. Correct or not?
Correct, sir.
Some heat would be lost into the surrounding because now your experimental setup is the warm object and the atmosphere is the cooler object. So heat is not going to get in like earlier, rather heat is going to go out because of the reason. So in this case, if you consider this equation, the Q value that you are going to calculate out from your power into time, all of that heat would not be used to actually boil the water. So the actual value of the measured value of Q that you are going to use is going to be somewhat bigger compared to the actual amount of water that was boiled, because some heat has lost to the surrounding. Or in other words, I can write that if the true value যদি আমি true value দিয়ে লিখি, মনে করো QT এইটুকু পরিমাণ হিট দিয়ে আমাদের অ্যাকচুয়াল বলিং হয়েছে, বাকি একটা স্মল অ্যামাউন্ট অফ হিট আমাদের অ্যাটমসফিয়ারে হারায় গেছে। না, disregard that. এটা দেখে তোমরা আরো কনফিউজ হবা, forget about that. Some amount of heat would have been lost to the surrounding, so the remaining heat was used for boiling. So in this case, the calculated value of Q, that total amount of that heat was not used for actual boiling. A smaller amount of heat was actually used for boiling. Can you appreciate this information?
Yes.
Yes, I understand, sir.
Which would mean, in this case, the numerator that you are using is somewhat bigger compared to the true value of Q that we should have used, which makes LV an overestimation. That is in the aspect, for the aspect of the Q part. এই পর্যন্ত বুঝা গেছে কি?
Yes, sir.
এটা হচ্ছে একটা পার্ট। আরেকটা পার্ট হচ্ছে এরকম, if we could insulate the setup to have 100% reduction of heat loss, if we could use all the heat that we are producing from the heater for exclusively boiling, no heat was lost to the surrounding, then the reduced mass reading would have been bigger, right or wrong? Because more mass of water would have been boiled if we could stop the heat loss. Which means if we could stop the heat loss, which means if all the heat that was produced from the heater over that time of duration, if the Q amount of heat that we are using in our calculation, this Q amount of heat was entirely used for boiling, the M value should have been bigger. Correct?
Yes, sir.
So if the m value would have been bigger, which means your calculated number should have been smaller. So your true value should be smaller than your calculated value, which means your calculated value is somewhat bigger than your true value, which means the LV is an overestimation because the Q that we are using is not entirely used, or if we could use the full Q, the M would have been a bit more bigger. So LV is an overestimation because heat was lost to the surrounding, and LF is an underestimation because heat was gained from the surrounding. This is the theoretical explanation. বলো
স্যার ওই m এর ভ্যালুটা আরেকবার একটু বলবেন, আমি এটা বুঝতেছি না, ওটা বড় কেন হবে?
বড় হওয়া উচিত ছিল যদি if we could use all the heat produced in the electrical heater for the boiling process. If we could
So
use,
sir, small reading কেন, মানে m এর ভ্যালু কম আসতেছে কেন?
because some of the heat is being lost to the surrounding. You cannot use 100% of the heat produced by your electrical heater for the boiling process. Some amount of energy is being lost to the surrounding,
পুরো মেসটাকে এফেক্ট করতেছে না, এভাবে চিন্তা করা যায়।
হ্যাঁ হ্যাঁ, বাট অরুণিমা বুঝছো কি বলছি?
স্যার আপনি বলতেছেন যতগুলা কিউ মানে যতটুকু এনার্জি দিচ্ছি সবগুলা ইউজ হচ্ছে, রাইট?
না, সবগুলো ইউজ হচ্ছে না। এই কেসে এলভির কেসে সবগুলো এনার্জি ইউজ হচ্ছে না, বিকজ কিছু এনার্জি বাতাসে বের হয়ে যাচ্ছে, বিকজ নাও আওয়ার এনভায়রনমেন্ট ইজ হ্যাজ এ টেম্পারেচার হায়ার দ্যান দ্য অ্যাটমসফিয়ারিক টেম্পারেচার, সো হিট ইজ বিং লস্ট আউটওয়ার্ডস।
না স্যার, সেকেন্ড কেসটাতে যেখানে কিউ কে আমরা ইনট্যাক্ট ধরছি।
হ্যাঁ, সেকেন্ড কেসে কিউটাকে ইনট্যাক্ট যদি ধরি, তার মানে হচ্ছে যতটুকু কিউ আমরা হিটার থেকে প্রডিউস করতেছি,
হ্যাঁ,
পুরোটুকু কিউ দিয়ে যদি আমরা ওয়াটার বয়েল করতাম, কোনো কিউ অ্যাটমসফিয়ারে লস হইতো না, তাহলে আমাদের এম এর ভ্যালুটা এক্সপেরিমেন্ট থেকে মেজার করে যা পাইছি তার থেকে কিছু হলেও বেশি আসতো।
কেন?
তুমি বলে easier thing, let's say you provided 100 joule of energy from the heater, let's say 20 joule got lost, which means you actually did boil 80 joule worth of water. That mass would have been smaller compared to 100 joule worth of water. From the experiment you are going to measure 80 joule worth of water, you are not going to be able to measure 100 joule worth of water.
আচ্ছা, হ্যাঁ,
বুঝা গেছে?
জি স্যার।
বিউটিফুল। সো এটা একটা জিনিস, আর এটা মনে রাখার একটা সহজ বুদ্ধি আমি প্রিয় স্টুডেন্টদের যেটা বলি, বিকজ ইট ক্যান বি এ বিট কনফিউজিং সামটাইমস বিকজ ইউ হ্যাভ এ লট অফ থিংস টু কিপ ইন ইওর হেড। সেটা হচ্ছে ট্রাই টু ইমাজিন আ পট দ্যাট ইজ টু বি ফিল্ড আপ উইথ ওয়াটার। ফিল্ড আপ উইথ ওয়াটার ইন দ্য সেন্স মানে হচ্ছে এরকম যে for the left scenario, for this scenario, heat was coming in, right? So the way I asked in many cases in the earlier years for the kids to remember, let's say if you have a pot that is half filled with water, you can pour in more water. So let's say that is sort of like heat is coming in and this level is under the top, so this is underestimation, just to remember by. Whereas in this case the heat energy was so big that it was flushing out, overflowing, so this was going outward, so overflowing, so this was overestimation. So water level is really going above, so overestimation. So this is another this is just a way to remember that in which case it's supposed to be overestimation or underestimation. Or some people also can remember it by that, well, lower temperature under hole underestimation, temperature higher hole overestimation, that can also work, but you shouldn't mess it up, and that's the logic behind it. So we're going to close our lecture for today's class. Thank you very much for the additional 18 minutes of attention. I really appreciate the 37 people left so far. We're going to stop the recording. If you have further question, you can ask me.